Stannate, zinc hydroxystannate, very useful as fire retardant, smoke suppressants. Very often the killer in any fire is not the fire itself, but the smoke. You get killed, choked by the smoke. So here you have tin stabilizers, tin retardants, which also suppress the smoke, and they are ideal replacements for the antimony oxide halogen systems, which are being looked at badly by the environmentalists. So the market is growing in this sector. There's no reason why Malaysia cannot make many of these. Easily make them. The new uses in the energy field, I'll just talk about the last one, lithium-ion batteries, the replacement of carbon cathode by the more efficient tin cathode composed of hollow tin nanospheres. It's very difficult to touch on everything, but basically I just want to give you a feel, a flavor for the range of applications that exist. Now to organotins. This is where much of the residence time will be. As I mentioned, there's an organic group attached to tin, and there's an inorganic ligand, like as halogen, hydrogen, or whatever. It doesn't, oxygen, doesn't matter. The organic group is typically butyl, methyl, octyl, or phenyl. Or sometimes you can have cyclohexyl groups for those who are chemists. Applications, catalysts in the manufacture of industrial polymers, polyurethanes, silicones, stabilizers for PVC, industrial biocides in wood and paint preservation, crop protectants, disinfectants. Let me take the example of polyurethane. Now, urethane is a carbamate ester which is formed when an isocyanate reacts with an alcohol. In polyurethane, you have multiple carbamate groups, and in this particular case, polyurethanes are used as moldings, coatings, fibers, adhesives, and so on. And the reaction is between a diisocyanate and a diol, and you need a catalyst, which is a tin catalyst. It can be inorganic tin or an organotin. The loading levels are quite 0.1 parts per very, very effective. And if you incorporate glycerol, you get cross-linking. If you pass carbon dioxide, you get a foam. As you see in the next slide, you get a rigid foam. This is for roof insulation, polyurethane foam. It contains tin. You may not believe it, but it does. Now, for the chemistry buffs in the audience, I need to explain this. There are several mechanisms. I think Tansri himself asked me this once. So for the benefit of Tansri, recap. Several mechanisms have been postulated, but this is one. The tin catalyst suffers hydrolysis to form a tin alkoxide, the tin oxygen bond, and the isocyanate inserts into the tin oxygen bond. And then immediately, very fast, it reacts with alcohol to regenerate the tin catalyst and the urethane. Silicones, they are already polymers, but you need to cross-link them or vulcanize them. The word vulcanization is familiar to most Malaysians because of rubber. You can vulcanize it at room temperature, RT means room temperature, with a tri-functional silane or tetra. This is a tri-functional silane. We have 3 methoxy groups attached to this cross-linker. This is the catalyst, this is the cross-linker. The cross-linker now interacts with the 3 molecule, 3 of this polydimethylsiloxane, and you get this curing taking place very fast. The 2 types basically in the industry. If you look at the industry, you look at the internet, you look at any of the booklets on silicones, you'll find RTV1 is not channel 1, channel 2 on television, it's RTV2. RTV1 means a one component mixture. You mix the polydimethylsiloxane, the cross-linker, and the organotin catalyst together, and presto, you get one product. Or you can the cross-linker and the tin is mixed separately and then added on to the polydimethylsiloxane, and you get that. So I won't bore you with that bit of the mechanism. This is how, for example, the encapsulation with RTV silicone. Silicone rubbers are used everywhere. RTV1 is used for gaskets, other one for resin molds. Again, the mechanism. Apparently, if you really use the diorganotin, diacetate, or any of the catalyst, anhydrous conditions, nothing happens. Obviously, the water is playing a role. The water is converting that into the hydroxyacetate, which then interacts with the cross-linker to form this compound, and then immediately reacts with the silanol to form the silicone. The largest application as catalyst is as stabilizing polyvinyl chloride, PVC. 75,000 tons of organotin stabilizers are used annually. And the PVC market is huge, 30 million tons. There are two types of stabilizers, one containing tin sulfur bonds, the other one containing tin carboxylates. Tin carboxylates are good for protecting PVC against light stabilization, whereas the tin sulfur catalysts are good against function as heat stabilizers. Now the octyl tin isoctyl, this particular stabilizer is so safe you can use it in food contact rigid PVC. It's safe for food as well. Nothing goes into it. The mode of action, again, the scavenger of HCl, replacing Cl, the defect sites on the PVC, and so on. No? That is going into real in-depth chemistry. This is PVC cladding. It's very efficient against, it doesn't fade with light. No ultraviolet deterioration of the PVC occurs. Now the biological applications of organotins resides basically with the triorganotins, as I mentioned, of this formula. In fact, they have been there for some time, since the 1950s. If you look at the early literature on tin chemistry, you'll find these compounds being mentioned, being produced. But the applications came later. Several have been commercialized: insecticides, acaricides, fungicides, marine anti-fouling agents, because of low mammalian toxicity. To be noted is this: organotin chemicals in commercial use have relatively low mammalian toxicity compared to many of the agrochemicals in present day use. So if there are people in the audience who think that, hey, are we introducing some toxic? Of course, to get the biological effect, you must have a toxic action. Okay? Otherwise, there's no point. But so long as it's not a runaway situation, it's okay. But if you compare that to many agrochemicals in use, you will be wondering why these guys are not removed. Where the R group is a phenyltins, they have low phytotoxicity, and the World Health Organization has approved these for agricultural use. Now the problem, I must be frank here, there is a problem with one category of compounds called tributyltins. I use the word TBT. That means 3 butyl groups. They are excellent as anti-fouling paints. Excellent. I'll show you why. But there is a problem. An environmental lobby has come up against tributyl. We are used to lobbying. You know, palm oil has a lobby. Every crop, every produce that comes out of any country, developing country, there will be a lobby out there. Even now to export timber, they will not accept your timber unless you replant. You know, so there are issues that we have to contend with. But let's be very clear about certain things. As scientists, we have to be very cannot be emotionally carried away by these so-called issues. So what we can do by way of research is how to reduce the so-called environmental impact on unintended targets. Some biocidal use of tin continues as wood protection and to prevent growth, moss growth in graves. Here you can see that this has been treated with tin. This is not. You can see it's very clear. Stone walls, sidewalks. In wood preservation, the tin is introduced in the quantity of 0.5 to 2 kilograms per meter cube of wood, and very often you can use double vacuum impregnation method such as this. And it's securely tied up into the wood, it doesn't leach out. And here is a ship. The hull is free of any anti-fouling species. It's excellent marine paint, marine fouling, anti-fouling paints. Now, I mentioned this problem, so let me come back to it one more time. Why this has become somewhat of an issue? The reason is excellent performance. I call it a case of a runaway success. It is supposed to have been used on ocean-going vessels, military, submarines. The American Navy still uses it. The Chinese Navy still uses it. Russian Navy still uses it. But now, despite all the so-called ban. But because it's excellent, for 5 years you don't have to worry about anything. Because if it's a smooth surface, you have barnacles, tube worms, seaweed, all sticking onto the side of the ship, and then to keep up the speed, you would increase your more fuel consumption, more pollution in the air. So they find it excellent, especially submarines. And you can see the leach rate is that. This is made possible because there are paints now containing a copolymer of methyl methacrylate and tributadiene methacrylate. This combination allows you to produce what are called ablative self-polishing anti-fouling paints. The runaway success is because it's so good and easily procurable, people were using it on marinas, yachts, in coastal areas. You should be out at the sea where the tin is being washed away. But they use it in yachts and moors and marinas and close corners. So the water, what happens is that some of the tin compounds go into the sediment. And this has had a bad effect, bioaccumulation in non-target organisms, shellfish and mollusks. The oyster people were up in arms because more shell and less meat inside. And in some cases, like gastropods, the endocrine disrupting substance effects on gastropods or mollusks. The snails sometimes even change their sex. But I don't think it's been tried on humans. Now, what is the exciting thing about organotins? Easily manipulated, not very sensitive to air. Laboratory synthetic methods, straightforward. And the source of tin is tannic chloride, organotin halide. And we have extended this, we have prepared this ourselves, we have extended it to a pilot plant scale synthesis. And even in the process, we developed a rapid speciation, high performance HPLC method for determining the purity of the intermediates and products with such low levels. So we can not only produce, we can ensure its purity, the levels of purity. That is the beauty of it. And this picture shows yours truly here. We have set up a pilot plant last time at the University of Malaya. We actually produced, I think Lo Kong Man, Dr. Proflo is somewhere here. If you can figure yourself there. Now, the interdisciplinary team, Organotin, which we initiated in the 1980s, extended in the 1990s, this marked the indigenous first effort of its kind in the country. Malaysia boleh, kita pun boleh buat penyelidikan di sini, of a standard comparable to any in the world. And we were the first to show this, that it can be done. And we were not happy with conventional tin compounds. We prepared new generation of compounds which were environmentally less harmful, more the patterns of toxicity or the